Okay, you guys in Zoom can see the screen okay?
Sure can.
Good. I'm also going to change the reset, I think. Okay, protocol suites. And really, there's really just one protocol suite that we really care about anymore, and that's TCP/IP. And that's the one we're going to focus on. There's something else we want to get up here. Ready to play. So hopefully this little table is somewhat familiar, even if it maybe looked, well, yeah, you probably, maybe this is a little bit different than what you've probably seen before. So just for comparison's sake, they throw in these other protocol suites, but none, the OSI, there actually was a protocol suite that was called, ISO, which followed the OSI model exactly. There was actually 7 layers of protocols that was used, if I recall, by Digital Equipment Corporation or somebody a long time ago, but it wasn't in common use. Apple Talk is long since, unless you've got some really old Apples that you're using, Apple Talk is as good as obsolete, as is Novell NetWare. So, but these, at one point, we had to support in a network TCP/IP, Apple Talk, and NetWare all at the same time. They're all 3 of those. We never had to support ISO. I didn't anyway. They're all 3 routable protocols, layer 3 and above protocols. And it was a much bigger pain in the butt to keep that type of network working. Nowadays, we just have to support TCP/IP, and which is hard enough, especially now that you've got IPv6 thrown into the mix. But at least we don't have to worry about supporting these additional protocol suites anymore. I suppose you might run into a network somewhere that's still using one or both, but I kind of highly doubt it. Okay, now TCP/IP. See, the other day I thought it was static, but I was nowhere near the desk, so I don't know why my PowerPoint keeps doing this, stopping and restarting, and haven't had time to try to troubleshoot it. So there's 4 layers that the TCP/IP protocol suite operates at, compared to the OSI model, which hopefully you remember is how many layers? 7 layers, yes. And these 2 map directly to OSI model layers. Transport, it's called the exact same thing in the OSI model. Internet protocol or internet layer, I also refer to as internetwork layer, maps to which layer in OSI? Just slightly different.
Data link.
No, I know. Internet, it's where IP is. Where does IP live in the OSI model layer? Yeah, well, just get rid of the inter part. Network layer, okay. So in OSI, internet is just called network layer. And that's where IP lives. And the network access layer is actually comprises 2 of OSI model layers, which are
Physical and data link.
physical and data link. The application layer comprises 3 of the OSI model layers, which is
Application, presentation, and session.
application, presentation, and session. Good. All right. So just because there's only 4 layers in TCP/IP doesn't mean that the functions aren't present. The OSI model functions aren't present. They are. It's just that, you know, they combined data link and physical, and they combined all the stuff that the session, presentation, application layer do into one. And that's really, it's not quite right to say that they combined them, because that kind of gives you the idea that OSI existed first and that TCP/IP just sort of loosely followed it and decided. Actually, TCP/IP existed first before OSI. So TCP/IP has been around longer than OSI, but OSI just sort of, you know, took what's going on there and decided to add a little bit more detail to, mostly for the purposes of learning, understanding, networking, but also development. You know, there's certain things that, for example, HTTP protocol does. It really does do some presentation and session layer stuff. It's just that it's all part of that HTTP protocol in the systems that use HTTP. But they they still perform the functions of the presentation and session layer. Okay, so to look at these, each of these layers has a whole bunch, or in some cases a couple, protocols that are part of the TCP/IP suite that function at that layer. So that means that, you know, FTP, HTTP, all these only do application layer stuff. Presentation, session, and application, we refer to the OSI model. Transport layer does transport layer stuff. And there's only 2 possible protocols. And in reality, as you'll see, in OSI, the transport layer has a fairly, you know, lengthy description of what it's supposed to do. It breaks data from the application layer into segments. It provides sequencing and reliability. Well, only one of these 2 does that. Does those things that breaking things into segments and providing sequencing and reliability. Which one of those 2 does TCP. Real transport layer stuff? TCP, right. So the fact that it's connection oriented is part of the formula of why it provides those capabilities. Without the connection oriented aspect, it would be much harder, as we'll see, to do things like reliability. And so UDP is kind of a pseudo transport layer protocol. It really doesn't do hardly anything that OSI describes as a transport layer protocol. So it's, let's say, transport layer light. And then the internet layer, you know, mostly we think about IP functioning at the internet layer, but all these other protocols, they kind of sit on top of IP. They're to say that they're at the same layers as IP. If you were to actually look at the packets, captured packets in Wireshark or something, it almost looks like ICMP is a transport layer protocol because it's actually got its own encapsulation, and IP encapsulates around it. But nonetheless, the functionality that these including the routing protocols, do are layer 3 things. One of the layer 3 functions is routing. And so, of course, routing protocols do routing. And ICMP is really, it's really just sort of like, let's say, an enhancement of the raw IP packet. And then NAT, is pretty much IP with just some added functionality where you do some translating of addresses. And then finally, the network access layer and the parts that are software are ARP, and sometimes really you'll see ARP as a defined in the network layer or internet layer. Sometimes you'll find it here. Some will even kind of put it where it's straddling both the network layer and the network access layer, because it kind of does functions of both, because it deals with IP addresses, right? Because that's what address resolution protocol is. It translates IP addresses, takes known IP addresses and gets what type of address?
MAC address.
MAC address, right? Which is the network access layer thing. So ARP does really, in terms of what it's doing, it kind of straddles the two. And again, different tables, different diagrams will show it in different places. And then these guys are really kind of hardware, Ethernet and wireless LANs. Those are defined in hardware. There's no real software other than, let's say, the driver that communicates with the network interface. But most of what Ethernet is and what wireless is, it takes place in the actual network interface, the components on the NIC. Okay. Sometimes this works and sometimes it doesn't. There we go. I guess I have to be closer. All right, TCP/IP communication process. So hopefully this looks somewhat familiar, where you've got these encapsulations. The data comes from the application layer, and then that gets sent down. This is from the sending side. So the web client has the data, sends it down the protocol stack to the transport layer. So that encapsulation or header gets put on. Transport layer sends it down to inter-network layer. So the IP header gets put on. And finally, down to the data link layer or network access layer, as TCP/IP calls it, and your frame header gets put on. And then when it gets out to the physical, it gets sent out as bits. So just to show this in a kind of animated type form, and you may have seen these already. I don't know if we're in CNT101 with instructor that might have shown you these, but it never hurts to see something more than once, I hope. Here we go. So this is just an animation showing data being sent and then received, and kind of what happens at each of the OSI model layers. And keeping in mind, of course, that with TCP/IP, you don't have separate pieces of software doing this. So TCP/IP if the application layer protocol is HTTPS, layers 5, 6, and 7 are packaged into that driver or whatever, that software module. If it's FTP, again, the top 3 layers are packaged into the FTP protocol. So let's see what that looks like. And sure is my sound on. Oops. All right. Got to check to see if sound was on. Although not very loudly. Let's see how I can increase the volume here. As far as it goes, is there a volume on this? Shoot. I should have checked out the speaker volume before. That's not even loud enough to hear, is it? What the heck? I wonder if there's a physical volume button on this guy. It's coming through here. Oh shit. That's not right. When do they use HDMI?
I think that's nice.
Huh. Crap. A digital link. There it is. So where is it? Let's see if that's loud. Is that any louder?
Speakers.
Oh, crap. Everyone be quiet. It also shows you up here what I'm saying there.
Try the restaurant.
Ceiling speaker.
Yeah, but I didn't see a volume control. Well, wait, there used to be a knob. Change this one.
Did we change that to the touch or is that still button?
Wait a minute, there is.
Damn techies.
Protocol data for PDU this way is just called data. The application layer sends the data to the presentation layer with any necessary format. Session layer, if needed, maintains the communication section. The PDU is still referred to as data, presentation and session layers. The transport layer breaks the data PDU into smaller segments if necessary, and adds port and sequencing information as needed. Segment is transferred to the network layer, which contains logical address information of the data packet. The packet is sent to the data link layer, which has physical address information, the source and destination microservices, and the CRC data frame. The data link layer also gains access to the media. The frame is passed down to the physical layer, which transfers the frame across the media in space. When the message arrives at the destination computer, the bits are read in on the physical layer and transferred up the data link layer's frame. The data link layer verifies the destination address, CRC, and trailer, and hands off the resulting packet to the network layer. The network layer verifies the logical address in the packet header, strips the packet header, and sends the resulting segment of the transport. Transport layer strips off the segment header, assembles multiple segments if necessary, uses the port number to determine which application layer server should receive the message, and sends the resulting data to the session layer. Session layer passes the data to the presentation layer and finally to the application layer. The application layer sends the original message to the chat program and the message is received.
All right, so, some of the key takeaways here. I gotta get that fixed. The PDUs at the various layers. So that's something that we'll be, talking about as we study each of the layers. But just remember that data at the top three: segment, packet, frame, bits. And ideally, when you're talking about stuff going from device to device, when you talk about stuff that's processed by a switch, a layer 2 switch, you refer to it as a frame. A lot of people use packet generically, and as long, people kind of get an idea of what you mean by that. But if you use that correct PDU name, then you sound a little bit more learned on networking. And then when you talk about when the information gets to the router, routers really, the frame header is only used by the router to say, is this intended for me or not? By looking at the destination MAC address. After it's determined, okay, this is intended for me, it strips that off and doesn't do anything with what's inside. Unlike a switch, which uses the source and destination MAC address to switch the frame from one port to another and to build its switching table. But routers just discard this and the CRC and just care about that destination IP address. And then once they've decided what to do with it, how it should be routed, then it'll route it if necessary. If the destination is on the same IP network as one of the router's interfaces, then it'll just deliver the packet. It'll put a new frame header on it and deliver the packet to the end device. All right, which is actually another animation that might show when we get there. So let's see if I can back to where we were. Okay, and this is what this static picture is kind of showing, although with less detail and only using the 4 layers of OSI. All right, so the reference models, that's now we talk specifically about OSI. And again, this is the same, more or less the same figure as before. It's showing fewer protocols at the application and data. It's showing some more at the data link and physical layer, wireless, SONET, SDH. In this class, the only data link layer and physical layer, let's say network interface layer technologies that we're going to care about are Ethernet and wireless. The wide area network stuff is talked about in I think the third class. So, and not even in that much detail. It used to be that frame relay and ISDN were, the WAN protocols that were in common usage out there, and those are pretty much legacy WAN protocols now. So SONET and STH and things like Metro Ethernet and others are, have taken over from those. Okay, so these are the quick and short descriptions of what each of the OSI model layers does. And, you pretty much have to, I wouldn't say memorize words in order or anything like that, but certainly have an understanding of what these words are saying. And even though we will look at each of these in detail, there's like a chapter for each, although I think there might be 3 chapters for the most important one for this class, the network layer. Real quickly, presentation layer, I think, application layer, its main job is to provide network services to users and the programs that they run. So the application layer is not the application. It's not the web browser, okay? The application layer is HTTP. If you're using a web browser, the web browser communicates with a service that's running on your computer, usually named HTTP or HTTPS, and your web browser communicates with that service. So the application layer, and HTTP is the application layer protocol. So application layer protocols are used, this says process to process communication. Yes, that's true, but really another description of it is that it provides services to user applications, user programs, just to keep the terminology separate. Presentation layer, just to kind of give you an idea that the presentation layer is part of the application layer. And here I'm going to, talk about the web browser actually doing some of this. One of the things that you might say that the presentation layer does is it modifies data as necessary so that the application layer can properly understand it, or that the end user program can understand it. For example, encryption and decryption. So if data is encrypted, it's the presentation layer's function to decrypt that data. So, that's why there's HTTPS. HTTPS part means secure, and part of that means that data is encrypted and decrypted. So a presentation layer does that data manipulation. It also deals with formatting of information like graphic files. If you're going from, let's say, a Windows system to a Linux system, some application layer protocols will fix the file if it's a text file, and they'll change the end of line character appropriate for the end system, because Linux only uses let's say, to use the character or the escape character representation. Linux uses a /n as the single end character, whereas Windows uses /r/n, carriage return line feed. So Linux basically takes /n, which is the carriage return, and basically just does both the carriage return and line feed, whereas Windows needs both. Needs a carriage return to move the cursor from the line, and a line feed to move the cursor to the next line. And some application layer protocols will fix a text file if you're transferring data between a PC in a Linux or a Windows-based system in a Linux system. Session layer, one of the main things that occurs at the session layer is meant to maintain communication between computers. So not computer applications or protocols, but actual machines. So when you, for example, access the Yale College website and log in, the login process is a session layer function. And as long as you're logged in, you can use any application that you're, have access to on that end system. Even if you're, using different transport layer protocols or whatever, the login will keep you having a session between you and the web server at Yale College. Does a few other things, but that's one of the, let's say, easiest to understand things that session layer does. Transport layer is what is meant to break your large chunks of data. Like, if you're transferring an MP3 file, you can't just try to send, 3 megabytes all at one time out Ethernet port. On your computer, you have to break that 3 megabytes into a whole bunch of smaller 1500 byte size segments. And that's what one of the things the transport layer does. But each of those segments also gets tagged with a identifier so that if they arrive out of order, and how might, if you're sending a big file, let's say across the internet, how might the data arrive out of order? How would that be possible? If you're sending them in order, segment 1 or packet 1, however you want to look at, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're sending them in order. How might they arrive at the destination out of order?
Getting mixed up with other traffic.
Okay.
Collisions.
What's that?
Collisions. Yeah.
Probably not so much collisions anymore. The collisions really don't happen in modern networks. I think what you said is a little bit closer. It has more to do kind of with fault tolerance in networks.
Sure.
Quality of
Multiple
service?
paths. What's that?
Quality of service?
QoS, maybe that might play a part. And there might be multiple things. The thing that most quickly comes to mind is when there's multiple paths to destination. So you've got, let's say out there on the internet, your data goes through your ISP. Well, they probably don't, unless they're a really small ISP, they probably don't just have one way to send your data out to the rest of the world, because that one pathway could, probably get saturated. So they probably have at least a couple, and depending on the size and how many customers they're serving, multiple ways to get out to the rest of the world. And then, your data goes from one ISP to another ISP to another ISP until they finally get to the ISP where your destination network can be found. And going through all those different ISPs, they're all going to have fault tolerance built in, multiple paths. So it could be that packets 1 through 10 they all go through the same routers to get to the destination. But then one of those routers at one of those ISP gets saturated with data. So what happens in a fault tolerant system, especially with protocols, routing protocols like OSPF and EIGRP, and BGP on the internet, is they will detect, this router is now, saturated. There's a big delay. So it'll send the data through another place. So packets 11, 12, 13 might go a different route, but then that first router gets cleared up, and now the next several packets go through the first router. And you do that enough, and they're invariably going to arrive out of order, because they're just taking, packets 13, 14, 15 might just zoom through the rest of the internet to get to its destination. And packets 8, 9, and 10 got delayed somewhere. They might arrive eventually, but they got delayed. So that's one of the key ways that that packets arrive out of order is when you've got multiple paths to the destination. Okay, and then so the transport layer is responsible for putting back into order and reassembling a big chunk of data that was broken up into smaller ones and reassembling it into that big chunk before it sends it up to the top layers. Network layer, just basically IP addresses and routing occurs there. Data link layer is basically, it's in a nutshell, its function is to deliver the frame to the end device. That's why you need the MAC address. The physical address, and that's why it's called the physical address, is the only thing that gets the frame to a particular device in the network. And that's its only job, to get the frame to the end device. Or in some cases, an intermediate, like going from router to router, the data link layer, gets it from one router to the next. But it really, its biggest role is getting it to the final destination device. Once the packet gets to the destination network. Okay, physical layer, everything that you can see and touch is defined by the physical layer, the connectors, the cabling, and then the one thing that you can't really see, at least not with a piece of equipment attached to it, is the bits. So the physical layer also defines the bits that are traveling along the media or in the airwaves or whatever.
Is the physical, as far as the physical layer and the media, is it always described as media typically?
Yeah,
They don't use other,
media
Right.
encompasses, copper cabling or fiber optic or wireless,
Right.
radio links.
but my question is they don't have other names that they would say, this is other transport stuff.
I don't think so.
It's all pretty much media.
Yeah, that's at least as far as what I've heard called. Yeah. And I think that's probably accurate. Okay, so, this is sort of somewhat smaller descriptions or more brief descriptions, but, this encompasses the top 3 layers of OSI. This is a 1-to-1 with the transport layer, 1-to-1 with the network layer, and one defines the data link and physical. All right, so data encapsulation. So one of the reasons that we segment the data, which is breaking it up into smaller units, is because a lot of it really goes back to the original Ethernet. And it's kind of a shame that we have to maintain backward compatibility with the original Ethernet, which was only able to do 1,518 bytes for a frame. Maximum frame size is 1,518. And we pretty much maintain that today. Although there are systems, switches, routers, end devices where you can set the frame size to what's called a jumbo frame up to like 9,000 some bytes. But the problem with that is all your devices in the path have to support that, and they have to support the same configuration of a jumbo frame. And so most people just don't use jumbo frames. Maybe in certain systems that just really need the speed. Because if you think about it, what happens with the segmented data, the reason that it was done in the first place was because you were on a shared media network with Ethernet and coaxial cable. You know, you probably saw the diagram where you had daisy chain your coax cable from one device to the next. Well, or when we transition to hubs, repeaters, same situation. Only one device could send at a time. Because if you didn't, if multiple devices sent at the same time, that's when you get your collisions, right? Well, you know, switches do away with that. They turn off the collision detection because you just can't have a collision on a switch because they work very differently than a hub. Well, because only one device can send at a time in a legacy Ethernet, if you didn't break up these large messages, large files into segments, you could have one device just completely hogging the network essentially. Because if they're constantly sending a stream of bits, every other device on that LAN, on that shared media LAN, is listening. And if they hear data being transferred, they're not allowed to send. So somebody that sends a 100 megabyte file, especially in the old days of 10 megabit or even slower, the original Ethernet was 2 megabits, then they're gonna have to just sit there and wait. And what about if it was, a gigabyte file? And what if one system is just faster than all the others, and so it can send multiple files so fast that the others, even though there might be a pause between files, the other systems may not have a chance to, get in there. So you had to have these smaller segments, smaller units of data, and a pause, a very, very slight pause. We're talking microseconds, but still a pause between each frame. And that pause would cause everybody that's listening to hear nothing, silence, and that would allow them to send. And of course, the first one wins, right? If there's 10 machines waiting, then the first one that hears silence and gets its frame out, it wins. But he can only send one frame and pause. So others will hear the silence and jump in there. And that's why you would, could have a fairly big network. I think I managed in the late 90s a network. All we had was hubs. We didn't have any switches yet. And we had probably several hundred computers on one shared media LAN. Our collision light on our hubs were just blinking like crazy. I mean, they were constant collisions because a collision is where multiple systems hear silence and they both send at the same time. And that's why you have the collision detection, is so that everyone says, oh, there was a collision, you got to resend your frame. And, but it somehow worked and seemed to actually work reasonably well. I mean, as our network grew and the speed of our computers got faster, hub-based or repeater-based networks, they started to fail. I mean, there'd be times where machines would time out trying to access the network, because the default standard of Ethernet is retry your frame 15 times. If you can't send it in 15 tries, give up and basically tell the operating system, I can't do it. And you'd get depending on the application you're running, some sort of error that there was a network timeout.
So the old collision detector, that just perpetuate more collisions? It's telling
Yes, it would. I mean, because you're basically having to resend the data, right? So that means you're basically sending more data.
Yeah.
And the collision takes time too, because the collision is a signal that gets sent out by the devices that detect the collision to make sure everybody heard that there was a collision. And so, yeah, it would quickly snowball into a network that would just freeze up if you had enough devices and there's enough collisions. So thank goodness for switches, because switches aren't shared media. As long as they're working full duplex, then that means they can send and receive simultaneously, and everybody on one port can send freely. and works a whole lot better because, you know, with full duplex, there's no collision at all. Well, I won't say completely. For the most part, there's no collisions. There can be a forced collision. I don't know that too many switches implement this anymore, but a switch, if it gets overloaded on one of its ports, it can actually send out a collision notification just to make everybody stop for a second and give the switch time to clear out its buffers and, you know, keep going. But that, I think, today rarely happens. Okay, so in any case, that's why we segment, and there's a complex reason why it's 1,518 bytes. It has to do with the amount of time it takes the frame to travel to the very end of the network through however many repeaters, the maximum of 3 or 5 repeaters, and the data to be, let's say, echoed back. And in any case, 1,518 bytes was the limit that you could have and have a working network with a whole bunch of repeaters in it. So we're kind of stuck with that because, you know, that's most Ethernet networks are still limited to that 1518. With today's switches, there's no reason really to have that limit. Now, the only potential reason, again, would be allow the switch to get a breather, so to speak, and clear out the buffers. Because if somebody's sending, you know, 100 gigabytes of a single stream of data, 100 gigabits, bytes, whatever, of a single stream of data to a single port, then the switch's buffers will get filled up. So there might be still a reason to limit the size of the frames, but certainly not at 1,500 bytes because, you know, that's super, you know, that happens in, I don't even know, certainly less than a microsecond with today's 100 megabit or gigabit networks. Anyway, so with segments, you got the delay, and that allows multiple devices and increases efficiency with these shared media networks. And it still can happen, though, that you lose a frame. And, you know, that can happen because somewhere in the path, either a switch or a router's buffers were full on the incoming port. And when that happens, they have no option but to just drop the frames until they can make room internally in the RAM for additional frames to be stored. And so when a frame gets lost, the only thing that happens is that the end device never gets it, and therefore they can't acknowledge the fact that they got it, right? If they don't get it, they can't acknowledge it. And so the sending device, the only way that they know that a frame was lost is because they don't receive an acknowledgement from whoever they're sent the destination for that, let's say, segment of data. And so they know then, okay, if I haven't received an acknowledgement in a certain amount of time, then I retransmit that part of the data stream. Doesn't have to retransmit the whole file, only the ones that got lost, that didn't get acknowledged. All right. So that's sequencing is, of course, to reassemble data that's arrives out of order. So there's a sequence number attached to every segment. And if they're not in the right order, then it's the transport layer's job to reassemble. So again, the PDUs are important to remember. Data segment packet frame bits as you go down the protocol stack. And with the TCP/IP, application layer is data, transport layer is segment, network layer is packet, data link layer or network interface layer is frame. OSI model, of course, frame and bits, physical layer, data link layer, and then data is defined in the top 3 layers: application, presentation, and session. Okay. All right, so you saw in that animation that it starts out as data, and with each successive layer that has its own header, it gets another encapsulation. And so it basically builds the frame with successive encapsulations. And the frame is called a frame because it's the only encapsulation that actually frames the packet. Because a header and a trailer, what's in the trailer? What's that called?
Cyclic redundancy check.
CRC.
CRC. And you'll also see it in diagrams. The CRC is the actual name of the calculation. The name of the field is usually called FCS, frame check sequence, and it contains the CRC. But whatever, either way, works. However you define it. FCS is the name of the field, which contains the CRC. All right. And again, on the receiving side, the receiving side receives the data in the same format that the sending side layer saw it as. So the physical layer sees it in bits because that's how the sending side, when it got to the physical layer, sent it. The receiving side, when it gets to the data link layer, it sees it exactly the same way in the frame that the sender saw it. Same with each layer until we finally get to the application layer, so that whatever the user program was, whatever was sent, whatever the data looked like when it was sent, that's the way it should look like when it's received. Okay, so layer 3, data access. Layer 3 is IP, pretty much. I mean, that's what we focus on. We do talk a little bit about those other protocols like ICMP, and later the routing protocols, but we only go into ICMP in any detail. We don't really dissect the routing protocols in terms of what their headers look like. It's really just IP and ICMP that we do that with. And then TCP as well, but at layer 3, just IP and ICMP. So source and destination IP address. And if you, strangely, I'm not sure why they did it this way. Maybe there was a programming reason, but if you noticed with the frame, which address comes first, the source or destination? Destination's first on the frame. It's destination address, source address, and then there's like an 8-bit field, and then was it 16? I can't remember. And then the packet header comes after that. With the packet, the source address is first, and then the destination. I'm not sure when they developed IP why they didn't keep it consistent. It would have, to me, made more sense. Now, I understand why in a frame the destination address comes first. Any thoughts on that? Why? What would be the advantage, performance maybe, of the destination address coming first in the frame versus the source address in the frame header?
Because it's got to know where it's going.
Well, it's gonna see the both. So what's the advantage of it being first?
Saves time.
Yeah, with certain switches, cut through switching, the switch As soon as it reads that first 6 bytes of the frame, it sends it to the destination. Well, it looks it up in the table, its MAC address table, switching table, and sends it out. After it does that is when it examines the source address and updates the timestamp on the switching table or fills in the data on the switching table if that MAC address doesn't exist yet. But it's just tiny bit faster if the destination is first. Probably not so much with routers. Routers are the ones that care about layer 3 stuff. And they do so much more than processing than switches do that the time probably wouldn't make a difference. I still think would have made more sense if they put the destination first just to keep it consistent. But they didn't ask me back in the 60s when they were developed TCP/IP what I thought about the order of things. So yeah, TCP/IP was developed in the late 60s. It was mostly in the, in the lab, so to speak. It came about as DARPANET, Defense Advanced Research Projects. So it started off as government facilities to communicate between them and research facilities like universities. So that's how it started. And yeah, the protocol was developed in the 60s. I don't think it actually was put into use until the early 70s, but we didn't hear about it until, mid to late 80s kind of thing. And then everybody heard about it by the mid 90s. Okay, so devices on the same network. We're going to look at what happens here with when 2 devices are communicating on the same network versus, and then later versus when the destination is on a separate network from the source. And again, I think I have an animation for this when we get to it. So, but I'll talk about it in static first. So when you have PC1 communicating with the FTP server, all PC1 needs in order to communicate with initially with the FTP server is, depending on what services you have running on the network, either the name of the server or its IP address. So, but it always ends up with the IP address, right? Because if it only has the name, then how does it get its IP address? In the TCP/IP suite, if I have a host name, but I can't really create a packet without an IP address, what do I do? What does my computer do for me?
DNS.
Not MAC address yet.
DNS.
DNS. Does a domain name look up with that host name, and the DNS server, hopefully, if it knows the name of the host, will send it the IP address. Then it needs what? Before it can complete that frame, it's got the IP address now, but doesn't know. No, it doesn't know this, right? How does it, in order to build the frame, which is the only way that PC1 can send it out to the switch to be delivered, it needs this, right? Which is the what?
Destination address.
Destination MAC address, right? And how does it get that? Somebody said it, I think. Or they said MAC address before, but what do they use to get that MAC address? What's that? No, nothing to do with subnetting yet, or a subnet yet. If I have an IP address, what do I need to get a MAC address?
ARP table?
ARP. I use ARP. So
So it requires requires elevation, so you need to run it as administrator?
Exactly. Remember that when you're doing labs, if you're not logged on as administrator, you need to start your command prompt. If you're going to mess with the ARP table, you need to run the command prompt as administrator.
In what scenario would you ever not want to log in as administrator if you're in there to mess around with stuff? Like, why would you?
Well, if you're in there to configure configure the system in some way, you might want to log in as with an administrator account. The rules of security say that you should only use administrative rights when you're doing something that requires it. So you shouldn't, although I do, I have to say, you shouldn't log in normally just to run applications and do your normal work with an administrator account.
Because you might break something on accident.
You might break something on accident, or someone hijacks your session. Now they have administrator account rights, something like that. Bottom line is, most IT people, if their account, they put their own user account into the administrator group, and so they've always got administrator. But if you notice with Linux, for those that have run Linux, most systems don't let you by default log into the computer as root, or some of them don't. Say most, because I don't know about that, but a lot of them don't. You have to create a regular user account to log in as, and then you can do an SU, switch user, or a sudo to get root privileges on the command you're going to run. But Windows really doesn't have that. They have a run as, which is kind of like sudo, but it's a pain in the ass to use, so I don't use it. Anyway, let me just explain this ARP thing. So there's my ARP table. I've got a couple of addresses. Man, learned that fast. Okay, looks like my I'm not going to be able to get rid of my default gateway MAC address. So let me think of a IP address that I can. Who's running their computer right now? Their desktop machine. Not okay. You're on the desktop.
Yeah.
So 172.31.209.1 should be your address, right? And you didn't see that address in my ARP table. ARP-A displays my ARP table. But now that I've pinged him, then you see, I see others, but you now see 209.1's MAC address. So before I could communicate with 209.1, I needed to learn his MAC address. And I store it in my ARP cache for a period of time. It'll go away after a while all by itself. It'll time out. But, if I keep on communicating with that device, it'll stay in there a little bit longer. If I, only communicated once, then it gets gone pretty quickly. So yeah, you need the MAC address, and the ARP protocol is what does that. It's always just the first packet that you need to, use ARP before you can send it. And since you now have it in your cache, all future packets going to that particular address already have that MAC address in the ARP cache. So yeah.
So the computer automatically sends out a broadcast?
Yes, I was actually just going to get to that. Exactly. So I don't know who owns 192.168.1.1, right? My computer doesn't know. If he did, then he would already have his MAC address, right? So my machine has to send out a broadcast to the entire 172.31.208/23 network, which is, or is it? No. 208/22 network. So I sent that broadcast ARP packet requesting the MAC address of 172.168.209.1 to everybody from 172.31.208 through 172.31.215 dot whatever. And only one person is going to respond, the person that owns that address of 172.31.209.1. But I don't know who it is, so I have to send it as a broadcast. So that's how we do, get communication done within the same LAN. So this is pretty much what we just talked about. This is the role of the data link layer. The NIC is what, has the MAC address. It's part of the NIC hardware, so to speak. That's about it. So the NIC will only read in the frame if it's got it. If the frame header has the destination has the same MAC address as the NIC on the device, or if it's a broadcast. Okay, it'll ignore any other frames that it sees. So if a frame comes with a different MAC address in the destination, it won't even get into the computer really. It won't go up the layers. The NIC actually has a little bit of intelligence, and it will basically say, no, I'm not accepting that frame, and I'm not going to bother my machine with it because it's not for me. So if it's got the same MAC or if it's a broadcast, and then certain multicasts. If we're running a multicast application and the MAC address matches that multicast application, then it'll also read it in. Okay, so on a remote network, so remember ARP is a broadcast. So if I'm on PC1 and I want to talk to this web server over here, so I get its IP address, let's say through, DNS lookup. I know or I might just have it, but I still need the MAC address to send the frame somewhere. Where am I going to send the frame in order to get it to this guy? So I've got sitting here, want to talk to the web server, I've got its IP address, but I need a MAC address to be able to send that frame out, because you can't just send a packet without a MAC address onto the wire. So what MAC address do I get, and where, and how do I get it?
From the switching table?
No, I don't. No, I don't communicate with the switch.
You communicate with routers?
I do communicate with the router, but I don't. What is my communication with the router?
IP address.
Okay, so
It's the addressing tables, right? And then
The IP addresses.
okay, but I still, if I'm going to communicate with the router, what do I need from the router?
IP.
Okay,
The
and I probably have that in my
default
default gateway configuration. So I have his IP, but then I also need what?
That's nice.
Well, I need
The router's MAC
the
address.
router's MAC address, right? Can't send anything out onto the network without a MAC address. So what happens is PC1 says, I need to talk to 172.16.1.99. Well, PC1 knows that his address is this 1.192.1.110. Web server's IP address is this. What that tells PC1 is web server's on a totally different network from me. I can't just send an ARP with that address and get the MAC address. First off, ARPs are broadcasts and routers stop broadcasts. This router, if he hears a broadcast, he will not send it along. He basically will look at the broadcast and say, well, if it's something that he cares about, he'll process it. But if it's, some other thing, he won't send it along down the line. He'll just basically drop it. So that's why you can't use ARP to get this guy, this MAC address. And think about it, if you could, in fact, the internet would be just clogged with ARP broadcasts, right? Because every time you tried to talk to a web server somewhere in the world, you'd have to send out an ARP and they'd have to go through countless routers and networks, all these broadcasts, right? And what do switches do with broadcasts? They send them to all ports. So everybody in the world essentially would hear your broadcast. The internet would die immediately. That wouldn't work. So recognizing that the web server's on a separate network, he says, all right, the only way I get this packet to my destination is to send it to my router. And then it's the router's job to get it to wherever that 172.16.1 network happens to be. So he looks up, he checks the registry if you're on Windows, look to find the default gateway, which is this. He sends an ARP out to his local network. The router will see that ARP request, send him his MAC address. And now he sends the frame to the router. The IP stuff stays the same. The IP stuff is still his address and his address. But the MAC address will always be the intermediate device. And then he'll do the same thing. He'll look up in the routing table and say, how do I get this to 172.16? Well, his routing table is going to say, send it onto this router, whatever router this is. And then he'll send an ARP and get a MAC address for this router. And then he'll do the same thing. Look up in his routing table. How do I get to this network? Send it to this router. He'll get the MAC address for this router, send the frame to him. And then this guy's attached to this network. So he will send out the ARP for the destination device and finally get the MAC address in the frame to be delivered to the web server. So like I said, I had an animation for that. And see if I can. I think. All right, so the changing frame header, hopefully you can hear. It does have subtitles though.
Packet header includes source and destination IP addresses.
Oh, did I pause it?
It remains the same throughout the journey. Computer 1 determines that the destination IP address is located on another network. So the frame must be delivered to Computer 1's default gateway, which is router 1's P0 interface. Computer 1 checks its ARP cache to see if router 1's P0 MAC address can be found. Computer 1 does not have router 1's MAC address in its ARP cache, so it sends an ARP request to retrieve it. Router 1 responds with an ARP reply containing the MAC address of its P0 interface. The frame is constructed using router 1's P0 interface as the destination unit, and Computer 1's MAC address is the source. Computer 1 sends the ping frame, which is received by router 1. Router 1 determines that the ping packet should be forwarded to router 2. To do so, the frame header must be changed with router 1's P1 interface as the source address, and router 2's P0 interface as the destination. Router 1 finds router 2's MAC address in its ARP cache. Router 1 constructs the new frame header calculating the CRC, and sends the frame. Router 2 receives the frame and determines that the frame packet should be forwarded to router 3. Router 3 finds router 3's MAC address in its ARC cache, instructs the new frame, and sends it. When router 3 receives the frame, it determines that the destination IP address in the ping packet is in the network connected to its network area. Router 3 checks its ARC cache and finds computer 4's IP address in its ARC cache. Router 3 constructs the new frame and delivers it to computer 4. As you can see, the frame header and CRC are changed at each router along the route to the final destination, but the source and destination IP addresses stay the same.
Okay, so, a lot goes on to get a single 1518 byte maximum chunk of information from one device to another, especially when there's potentially a bunch of routers in between. It's amazing that, it all works fairly quickly. But the devices are, that's the one thing, routers and switches they're computers, but they're very, very specialized computers. They have one job to do, and that's routing if you're a router, switching if you're a switch. So they don't have to worry about, GUI user interfaces or running any high-level protocols or anything like that. So they can focus on, their main task, and they do it very quickly and efficiently. All right, let's take a break now. I kind of went long compared to how much I usually want to go into a break. So at 1:15 by that clock, that gives you 10 minutes. If that's good, we'll resume.
Greg, you mind if I pick your brain? It's about my CNT140 class. My attendance here is showing 0%. I missed.
Kinda interesting,
when I clicked
guys.
on it. Absolutely. Thank you. Shows I missed one day, August 14th, which is true. But does that mean I should have a 0%?
Well, did he count attendance as part of your grade?
I'm not sure. I don't remember.
I just follow the
If you go to grades,
I'm not there yet.
then
Apparently neither is the specialist.
It's not here.
yeah, then that means
It
it
doesn't.
it didn't factor. So I
Okay.
wouldn't worry about it.
Okay.
I don't factor attendance into the grade either, usually in rare cases, so that's not affecting your grade. Some other stuff might, but
Yeah, it's,
It's- might be a situation where I have to get Kurt on the phone, because he's only teaching at the high school this semester, or the last 8 weeks, so.
I noticed here, there are 4 assignments labeled assignments here.
Mhm.
The total points for those only equal 196. I scored 85 points on those assignments, but it's only showing that I scored 65. And then there's, and where's the rest of that 176 points at? I don't even see an assignment on here that I could do to get the points. Cause I
Yeah,
did
no, I
everything.
understand what you're saying. Yeah, I'll, could you maybe send me a screenshot of that last part there? Because I don't think you can screenshot it. Just so that when I'm talking to him.
Yeah.
So, and you're one of the ones that got dropped from,
Yes.
yeah. So I think there might be a flaw in the system. Because normally if you were given an incomplete grade and you were given extra time to finish coursework.
Mhm.
When an instructor fills out the grading at the end, they put an I in for your grade, and then they supply a date as to when the material needs to be completed, so their grade reverts back to whatever you've earned up to that point. And it could be this automatic dropping from not having the prerequisite is kind of something they didn't used to do, or they didn't do it very religiously. So it could be that it's not factoring in completes. And do you know how much time, like, did you agree on a period of time that you would have to complete the material?
Yes, the deadline was today.
Okay.
I did my final exam on Tuesday and then turned in my skills exam Tuesday night.
So possibly he didn't enter the new version, the new grade. And if it was, less than if the previous grade was less than passing, then the registrar system probably said, oh, this person didn't pass CNT 101, they're not allowed to take this class. So I have to talk to multiple people, Kurt and the registrar, and try to get it. Because I can get people reinstated when crap like this happens. So I'll try to get that done tomorrow.
Still take the class if we count 101.
I'd have to get, got locked. Yeah. Sometimes someone leans into a button, which is good.
I also have questions when you have time. Just the Netacad thing. So like, they're doing the modules or the projects, whatever, like the auto grading thing. Like last night, I did
PK
this
calls,
one
yeah.
and this one, and it said in packet choices, it says complete whatever your grade might change depending on your answers. So that where it's asking me, what does this say? Blah blah blah. I need to type that out and send it to you, or no? That so like I'm getting the grade from Netacad for those.
No. I just don't. I don't grade those. Like, there's no place in Packet Tracer to enter those answers, right? Something like
Right.
that. So I don't grade that part of it. I only grade the part that the PKA file auto grades. So you should see a progress thing and tells you what percentage of the grade that you got.
Right.
And that's all the good. So if you got 100% on that, you'll get 100%. If you got 80% on that, you'll get 80%.
Right, but it's automatic, right? I don't need to do anything else.
You don't need to do anything else. Just save the file and send me that file.
Save the file and send you
The
file.
PKA file, yeah. Yeah, because that's the only way I'll know what your grade is I open up the PKA and see what it says. Because it'll keep your keep your results.
So I have to
When you
redo
save-
them.
Did you not save it? Because usually when you go to quit out a packet tracer, it says, do you want to save this file? And if you said yes, then it's.
Yeah, no, I'm just so used to not saving my progress from CNT 101 virtual machines. Like it's like never save anything. So I guess I thought it was automatic in Netacad.
Well, it would be good practice. Because there's not that
Yeah.
many commands you gotta enter, right?
Yeah, well, I still screw them up. So
Well, better reason to have more practice.
like dude, the password thing, I didn't do the $sign and like I didn't do the exact password they want. I just did Cisco like we did the first day or whatever.
Yeah.
So just do Cisco. I didn't do the special characters. And so it was like, you're not done. And I was like,
Oh, okay.
it was a shit show. It was fun though.
Yeah, well, what password was that it was asking for something besides Cisco and Cloud?
See, to elevate the, so there's,
Enable password?
there's let me in, and then there's enable,
Right.
which is Cisco, but it's C1
Oh,
dollar
really?
sign.
Okay. I guess they're probably just having you do that to show that you should use a more complex password.
Right,
But I don't need to get into the file. Like, I don't need to get into privilege mode at this point. It's only later when we're doing more complex networks and also on the skills exams where I actually need to get in and see what you did. I mean, the skills exams are auto grading too, but sometimes, someone says, well, I thought I entered the answer exactly like it's supposed to be. And I look and like, one letter is, you typoed something. And
right.
so I like to go and see, all right, I'll give you that. I don't care too much about typo. So on those, I need to get in there, but for the packet tracer labs, generally I just look at the score, unless there's some reason you need me to, like in order to give you feedback, I might go in and say, oh, you forgot this, you forgot that.
Right.
So, but on these early ones, there's usually not much of that.
So like, there's nowhere to submit this, right?
Should be. Is it under, well, wait a minute, is that one that's under assignments or?
No, it's just.
Oh, no. The only ones that
it's all
you
these.
submit are the ones down under assignments.
Right, so my question is, am I getting grades for these?
No.
Or I'm just doing.
The only
these
one you're
because I
getting
need the
grade for
skills?
is 291.
Okay,
If you scroll down, only if it's under assignments do I grade it.
okay, so I don't
The
need
other-
to send.
You don't,
Okay.
right. The only ones that you need to send me are the ones under assignments.
Okay, and
Because those are the only ones you can't send me.
I'm just doing these because I need these skills to get to the next assignment.
I have you do most of the packet tracer labs because, if I had to grade 6 or 7 for times 30 students, that's all I'd be doing.
Yeah.
So I only pick out certain 1, sometimes 2 that I put under assignments, and those are the ones you turn. So when you're doing 2-9, always look before you start doing them all, what's under assignment, so you know which ones to save and submit.
Okay. That clears up a lot, thank you.
Okay, yeah.
I got more gray hairs over that.
Okay, I think we're ready to move on. So network layer address. So again, the network layer address, which is the IP address, tells not PC1, it does 2 things in this scenario. It tells PC1 that the destination it wants to talk to is on a different network. And it tells the router what the destination network is that it's supposed to route the packet to. So that's pretty much the purpose of the layer 3 address. And then, of course, destination address, and of course, source address, same thing, except it's used for when a reply is sent by the destination device. So it's basically the same thing. He just puts PC1's IP address as the destination, makes his address the source, and the exact same process occurs except in the opposite direction. All right. That's about it for that. All right, I think they broke up what I already described with the changing frame header. They broke that up into these multiple slides, but just know that. So here's a question though. I said that PC1 has his address, and the web server, he looks at his address and sees that the web server's address, and he sees that they're on separate networks. Well, how does PC1 really know that it's a separate network?
Different network ID.
Because of different network ID, right? So if this is, hey, Zoom lane can't see this. Let's see, I'll try this since I've got it out here. I'm very, my writing will be very sloppy, but
Maybe raise the screen and write on the board.
yeah, they still can't see it very well. Well, I just want a blank one. Oh, blank. All right, so PC1, wow, it's slow when I'm zooming it. PC1's 192.168. Whoops. .1. And the web server is, let's just say the web server is not that, because 172.16, whatever that was, is obviously and clearly a different network. What if it was this?
That'll be the same network.
Okay, so hopefully you can read it. 192.168.1.1, 192.168.2.1. So how does PC1 know that 192.168.2.1 is a separate network from him?
If it's a class C, then the three
Different net mask.
octets would be different.
So yes and no, or it depends on the subnet mask. The class of the address, by default, yes, you're right. Since it's a class C, then it's the first three octets that determine the network ID, but you can change the subnet mask. If they had what if they had a /16, a 255.255 subnet mask, which meant that only the first two octets were part of the network ID, then they would be on the same network, right? So it really depends on the subnet mask to tell them what their network ID is. And so if we do have the standard /24, okay, now he doesn't know what the web server subnet mask is. He has no clue. So best he can do is basically say, well, my address is this. After he does the binary AND with the /24 subnet mask, which is 255.255.255.0, he'll end up with a network ID of that, 192.168.1.0. And he'll do the exact same binary ANDing with the destination address, web server's address. So he'll end up with, for the destination of the network ID being the 192.168.2.0. So clear, then he compares the two. And since they're not the same, then he knows, okay, 192.168.2.0 network is on a different network than me. But what if instead, because that's the whole idea of subnet masks, is that you don't have to go by the class. You can put whatever subnet mask you want, as long as it's at least /8. So what if it was /16, which is 255.255.0.0? Now the network ID is 192.168.0.0. And that would be the same for the web server. So now in that case, if this was the subnet mask, the two networks, they're the same network ID. Because he would basically do a binary AND with 255.255.0.0 on his own address, get 192.168.0.0, and do the same thing on the web, 192.168.0.0. And so then he would do an ARP, assuming that the web server is on his own network. So that's what's really important, is doing that calculation, that binary ANDing with its own address to determine his network ID, and doing the exact same calculation with his destination address. And that's what determines, is it remote or is it on the same LAN? You can't go by, obviously if it's 192 in the first octet and 172 in the first octet for the destination, that's clearly different. But when they're similar like this, and again, the PC, the computers don't say, well, that's clearly different. They don't make that lot. They still do the calculation, even if the first octet is vastly different from each other. They're not, they don't have, let's say, reason to say, well, I don't need to do a binary AND here because clearly they're different. They still do that binary AND for every communication to a different device. You only have to do it once and then send all the packets, to the place they're supposed to go to. Okay, so once he determines that the destination is on a separate network, he gets the MAC address for his default gateway, either from his cache or from doing an ARP, and sends it to the router, and the route is from there on in. PC1 has no control over what happens with this packet. It's up to the routers to get it to the final destination. And I think pretty much all this is been covered. If there's anything being said here that I haven't already said. Anybody disagrees, please raise your hand. If there's anything in here that you need explanation on. All right, that was it for module 3. I'm not going to let you off this easy though. So even though we're only supposed to get through 3 today, since we're not doing labs today, I think I want to at least start, not too much, because I know more than 2 hours of listening to me gets tiresome for me too. But it's not a bad idea to get ahead, because we invariably, something happens and we lose a day, whether I'm sick or spend a lot more time doing subnetting, which we often do spend more time than I a lot to do subnetting.
Right.
It's not a bad idea for us to get a little bit ahead of things. I think the next chapter is the physical layer, which isn't too exciting, not too much material there, but we'll get it started anyway. So I'll go ahead and start module 4. And we'll at least get it. Some slides. I don't know how many I knocked out, but some for sure. And like I've said before, just because I cut down the PowerPoints doesn't mean you shouldn't read the material. The slides I don't cover, because they may be on a quiz or a test. I just usually like to hit the stuff that is most pertinent or that needs review some of the stuff, it's basic, really basic, and maybe some people need review, but it's not enough, in my opinion, to, spend a lot of time on it in class. But you should, if something in a module isn't sounding like review to you, you should definitely read it, for your own edification, even if I would go over. All right, so we're going to look at the physical layer, its purpose, and then talk about some physical layer characteristics. This is really kind of dry stuff. You had this in the media chapter in CNT 101. So I'm really not gonna, I'm gonna try not to, just pour over every detail, because hopefully you remembered at least some of the key points of media. All right, so the physical layer is obviously at the bottom of things, layer one, in terms of the OSI model, or it's the bottom half of the network interface layer for TCP/IP model. And the PDU that we say is handled by the physical layer is bits, transports bits across the network media. So bits aren't technically, or at least we usually don't think of them as like an additional encapsulation. But you'll see, I think even in this chapter, that the bits that go out onto the frame, onto the media, the first bit that goes out there is not the first data bit. There is actually a form of encapsulation. It's called the start frame delimiter. So there is, in a sense, an encapsulation, because there's a special stream of bits that get transferred in front of the first data bit. And it's basically a heads up to the receiving device to say, a frame is coming. Because Ethernet is not a synchronous protocol. It's asynchronous. In other words, a synchronous protocol is where both sides have like a clock, and they can only send data based on, certain ticks of the clock. And so the receiver knows exactly when to expect the next series of data. Where with Ethernet, it's just send a frame, and hopefully the receiving device is awake and will grab it. And that's what the purpose of the start frame delimiter is, to basically give it a heads up. Hey, here comes a frame. Okay, so physical layer standards talk about the physical components. Those are usually like the TIA, EIA standards that define things like cabling, category 5, category 6 cabling, and RJ45 connectors and things like that. That's typically defined by TIA, EIA, and then the other is like IEEE. IEEE primarily is involved in, what do your signals look like, and how do we represent bits on the media, which is the encoding. So physical, the stuff that you can see, the network interface, connectors, the cabling, that's all part of physical layer. And then what's encoding? Encoding is simply the way that bits are represented on the media. So for copper, it's going to be electrical pulses. And it's basically going to be a voltage level that, if a certain voltage level is, if we're going from a low voltage to a high voltage, this is what this is. This particular encoding, which I believe is, this is Manchester encoding, the most simple encoding there is. No modern Ethernet networks, unless you're running 10 megabits. 10 megabits Ethernet used Manchester. Real simple, basically one, for every, you know how they talk about frequency of a signal? Well, with a 10 megabit copper Ethernet, the frequency was 10 million, 10 megahertz, 10 million bits per second. So each one of these lines is a 1/10 millionth of a second. So a 0 in Manchester encoding is defined as going from a high voltage to a low voltage. And a 1 is defined as going from a low to a high.
So for fiber optic, would that be like?
Fiber optic is just, fiber optic won't use Manchester encoding.
No, I mean
It's
zeros.
basically light or no light. Now, I believe that there might actually be some encoding with fiber optic in order to get more bits out of out of the frequency of light strobes. Let's say, for example, and this is not my expertise at all. 4B, 5B basically tells me that 5 bits can be represented in 4 clock cycles, and 8B, 10B, 10 bits can be represented in 8 clock cycles. Those are much more complicated encoding schemes, and I don't, I know what Manchester is just because it's really easy, and that's the only one that I cared to study a little bit. I don't really know those others. I've looked at them, but forgot what the details are. It's not really important. You kind of just need to know what encoding means. It just means how bits are represented on the media. I just wanted to show you this example just so that if you get into, network engineering instead of IT, then, this stuff becomes very relevant. For IT people, we don't care. I mean, we don't put oscilloscope. This is the only way you'd see this, is put an oscilloscope on the physical line and seeing those, highs and lows on your oscilloscope. And we don't do that. There's no reason to. We're not troubleshooting at the signal level in IT. But if you're a network engineer developing a new 10 gigabit Ethernet card, yeah, that's when you need to know this stuff very well. So anyway, that's what this is showing you. Transition from a high voltage to low voltage represents a 0, from low to high represents a 1. And the way that you get 2 bits in a row is that if you see in these 2 time frames, the transition comes in the middle of the time frame. The from low to high to low comes in the middle, low to high. So that basically allows you to just represent a single bit, or 2 different bits, a 0 and a 1 in this case. In this case, where we want 2 zeros, our transition from high to low occurs in the middle, but then we do another transition at the beginning of the next time frame in our second high to low. So this transition is not counted as anything because it's not occurring in the middle of the time frame. Because that's what Manchester encoding requires, is that the transition to count as a bit, it has to occur in the middle of the time frame. So this transition here is nothing, and it's only done so that you can go from high to low to represent 2 bits in a row, and same 2 0 bits. And then same thing here, we go from low to high in the middle of this to represent a 1, and then we do another, beginning of time frame transition so that we can once again go from low to high to represent that second bit. Again, that's the simplest of encoding that you'll see. If you look at 4B, 5B, 8B, 10B, it's a lot harder to follow. So, but that's encoding. It's representation of bits, how bits are represented on the media. Nothing more. That's about all you need to know about them. You're not going to get a question that's going to show you a square wave like that and ask you what bits are which. Okay, so some, all of the bandwidth abbreviations, hopefully this is all pretty well known to you, BPS. So just so you know, because a lot of people don't know this, bits per second is always represented with lowercase BPS. All three letters are lowercase. Bytes per second, which you'll see when mostly talking about throughput, is capital B. Yes. So lowercase b is bits, uppercase B is bytes. That's how they were able to distinguish between bits and bytes because they both start with B. What's a half of a byte?
4 bits.
What's the name for it? Come on, these IT people, they think they're really cute.
Byte.
What do you do if you don't take a whole bite?
Nibble.
Nibble, exactly. Spelled with a Y, traditionally. I have seen it spelled with an, as the word nibble, but generally it's NYBBLE.
That's a half of a bit.
That's a half a byte, 4 bits. 4 bits. Which why do you care about a half a byte or 4 bits? Well, that when we talk about hexadecimal, every hexadecimal numeral is represented by 4 bits, a nibble. Anyway, so hopefully all this, your bandwidth stuff is familiar to you. K and M, and G, and then now terabit. Latency, throughput, and good put. So a lot of times throughput and good put are maybe good put isn't even used in conversation. Most people just say throughput, but they do distinguish between them, at least Cisco does. So first off, latency. Latency is just the delays. Remember, there's a delay between frames. When a frame arrives at a switch, it takes some amount of time for the switch to read the frame in, switch it to the outgoing port, and have it go out. It's a very small amount of time, probably in the order of nanoseconds, but it adds up, especially with thousands or millions of frames being sent. So latency are just the delays that occur naturally. Buffers get filled up, frames sit there, or packets sit in router buffers waiting to be routed to the outgoing port, things like that. There's a very small amount of delay just traveling across the media. So, that's what latency is waiting. Throughput is the number of bits that can be transferred. So that's just the raw number of bits. So if you're running 100 megabit Ethernet, then your throughput is 100 megabits. Because whatever the media or whatever the network interface and the media, whatever they're connected at between, I should say the network interface and the end device, the switch usually, whatever they're linked up at, that's the speed that data is transferred. Okay, it's always going to be 100 megabits or gigabit. That's how fast the NIC spits out the bits. And then good put is actually how much of data that we care about is transferred over a given period of time. So good put includes your latency. And I think I'd have to verify this, and maybe someone that read the curriculum thoroughly can tell me. I believe that when they say overhead, they also talk about headers. So when you talk about a 1518 byte frame, 58 of those bytes are nothing but overhead. They're the frame header is 18 bytes. The transport layer header is 20, and the IP header is 20. So that makes 58. Yeah, 58 bytes. So for every 1,518 byte packet that's sent, only 1,460 of it is actual, possibly user data. And not all frames are 1,518 bytes. You might have a frame that's only has 1 byte of data and 58 bytes a header.
So does traffic overhead only refer to the stuff that's not data or?
I believe this is talking about, throughput, which is the measure of the bits, including the latency, and then minus the traffic overhead, which is the headers typically. So good put is how much of the data that I actually care about is being transferred over a given time. So usually, like when you're sending a file through a web browser via HTTP and you see the progress thing, I don't know if it's a pop-up or somewhere on the footer or something, you see the progress of the file that's being transferred. That's really measuring good put, because it's really measuring how much of the file is being sent, because it doesn't really, the web browser doesn't know about the headers and all that. That's the HTTP and TCP and IP's job to worry about headers. So your good put is when you actually see, how many bytes are being sent. And good put usually is measured in bytes as opposed to bits. Throughput is very often measured in bits, but good put tends to be bytes. But look at it, capital B or lowercase b. Okay, cabling, UTP. Why do we have twists?
To eliminate crosstalk.
Right. So how does it do that? Like why do twists help to eliminate crosstalk?
Wonder.
What's that? You were wondering?
Question. Yeah.
Yes, we wonder.
Okay.
Good question.
Magnetic fields,
Yes. What about the magnetic fields?
they cancel each other out.
Because exactly, different polarities. So it's called a differential signal. Ethernet uses a differential signal, meaning that on the orange pair, let's say, depending on how you've got things cabled, and if it's which type of device it is, a MDI or MDIX device. But in any case, let's say the orange pair is doing the sending. And let's say bits are represented by positive voltage. Well, in a differential signal, let's say the solid orange pair will carry +5, and the striped orange will carry -5 volts. And two different polarities, the electromagnetic fields cancel each other out, and therefore there's no electromagnetic field to bounce onto other pairs of wires.
So is the solid wire always positive and the striped always negative?
No, I don't know if I've got that right. It doesn't really matter. It's actually no. It's white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. So the first wire is the positive. The second wire is the negative. So in this case, the striped would be positive. It doesn't really matter. I was just really explaining the fact that it's differential. So that's how that works. The other thing is, so you've got the cancellation effect, but you also have the fact that since the one is negative and one is positive, what the receiving side does is it takes the positive voltage and subtracts the value of the negative voltage. And then, maybe let's say divides it in two or something. So let's say a 1 bit is represented by 5 volts. And I need to figure out how to use my pen on PowerPoint. Maybe will this annotate work?
Your writing was getting noticeably better.
Do you know how to do that?
Can I do this?
Do his pen on the power.
There you go.
So 5 minus 5. Okay, so that's a perfectly good signal. You got +5 on the positive line and -5 on the negative line, and they're subtracted by the receiver. What's 5 minus -5?
And
+10, right? Okay. So on the receiver, he sees 10, let's say divides it in 2, sees 5. I got a 1 bit. Well, what if there's noise? Electromagnetic interference always presents itself as positive voltage, not negative, always positive. So if there's noise in this signal, we now have, let's say we have 2 volts of noise. Well, that 2 volts of noise gets added, hopefully, the same to both wires. And the reason I say hopefully is because it's not a guarantee, but that's another reason why they're twisted. Because they're so close together, the likelihood is that EMI is going to affect both wires the same. So you want them to be tightly twisted. And that's another reason why when you're punching down in a patch panel, a maximum of 1/2 inch of exposed wire, untwisted wire outside the jacket. Because as soon as they're untwisted, now that EMI can appear differently, have a different voltage effect on the 2 wires. So let's say everything is terminated good and we get the same voltage on both wires. So now we have at the receiver 7 volts, and -5 + 2 is going to give us -3 volts. But remember, we're subtracting. 7 minus -3 is
10.
So the differential signal cancels out EMI, but it also allows noise to be subtracted out. So it has both effects. And it works pretty good because I rarely see, I don't think I've seen in a long, long time. You can go into routers and switches and look at the interfaces and they'll show you statistics on errors, and almost never see a frame with like a CRC error. And that's what would happen, if a bit is out of voltage range to be either positive, either a 1 bit or a 0 bit, then it'll get ignored. It'll just get tossed. And that'll cause the CRC to be wrong. Because if 1 bit is wrong in the frame, the CRC will be wrong. So, and you almost never see that. Usually a bad CRC is almost always a result of noise. And it could be a faulty NIC, but most often noise. Okay, so there we go with the UTP cabling. And how do I undo annotation? Can you just quit? Oh, but it's going to keep it up there. How do I get rid of it? There's probably an erase on there, wasn't there? Undo, yeah. It's probably a clear too, but okay. Shows you how much I use this kind of stuff. All right, connectors, nothing really interesting here other than the fact, you've seen these connectors and cables. except for, that's bad. And,
That wouldn't even work.
it very well would work, possibly. But there's no strain relief. So if somebody just, tugs on the wire, it's probably going to pull the wires out and no longer make contact with the contacts up, these contacts here. So that's why you need the strain relief there. But the other problem with them is that you've got some untwist here outside of the jacket. That's not that much, but still potentially, would cause some crosstalk or interference to be present. But the biggest problem is no strain relief. I think that's probably the biggest problem. And straight through and crossover cables. So straight through cable, both ends are terminated the same. They're both either A or B. And the only difference between A and B is the orange and the green. They're swapped. Crossover cable is you terminate one 568A and one 568B. And the thing is, this is only showing a crossover for up to 100 megabit Ethernet. Gigabit Ethernet, as you know, uses all 4 pairs. So for gigabit crossover, you also have to cross the browns and the blues, or else it won't be a proper crossover because you need the browns and blues are used in the transmission on gigabit. All 4 pairs are used. So just swapping the oranges and the greens like this picture shows would not be a crossover that will work with gig. Says crossovers legacy. For the most part, there's still devices out there that don't do auto MDIX, which is it senses whether you if you have transmit going to the transmit pins going to the transmit pins, then auto MDIX will flip the transmit receive pins. So when you have all auto MDIX devices in your network, you don't need crossover cables because the hardware will do it for you. A rollover cable is something that is, you probably won't need to make those. Cisco sends them out like candy when they send you a device. But a rollover cable has a peculiar pinout. It's basically whatever you want to do with pins 1 through 8 on one side, do it. I mean, it doesn't matter. You don't have to do 568A. You could just do, stripe green, stripe orange, solid orange, stripe. You could just do them that way. The other side is just the opposite. So in other words, pin 1 on one side has to be connected to pin 8 on the other side. 2 has to go to 7, 3 to 6, 4 to 5. That's what a crossover a rollover cable is. But usually we don't make those unless we happen to somehow run out of them. Fiber optic. It's immune to EMI RFI. It's immune to crosstalk. It is immune pretty much to eavesdropping. With copper wire, since electricity gives off a electromagnetic signal, even though it's canceled, I don't know. Presumably, you can still detect the electromagnetic if you've got super fine equipment that's able to, all you have to do is be close to the cable. But more likely for copper, you'd put something in there that physically makes contact with the transmit and receive wires. And if you did that, you could go undetected. I mean, you might cause some issues with the, you might get some packet errors because now you're introducing something that could, bust the electromagnetic interference qualities of the twisted pair. But you could come up with a device that makes contact with the wires, and now you can basically eavesdrop on what's going on there. With fiber optic, you really can't do that because you'd have to physically cut glass, reroute it through your device, and then reroute it again so that the connection isn't cut. And because if it's cut, then there's nothing going to be transmitted in a very short period of time. And now what use is that? And so you'd have to know how to splice fiber optic cable in a matter of, half a second in order to, be able to eavesdrop on it and get away with it. So it's more or less immune to eavesdropping. Uses lasers or LEDs. There's two types of fiber. There's multi-mode and single mode. Single mode uses lasers, multi-mode uses LEDs. The LED, the multi-mode is much shorter. It's measured in 2.2 kilometers or something is the maximum distance, whereas single mode can go tens of kilometers. It's a pretty complex thing. Hopefully you saw some of this in 101. You've got actually two pieces of glass, the core and the cladding. The core is what actually carries the data, and it's super, super skinny, 9 microns on single mode, a little fatter, 62.5 microns in multi-mode. But and the reason it's much smaller in single mode is lasers are being used for that, and lasers, are much more focused light than LED. So the purpose of the cladding, and again, if you only see the core and the cladding if you've got a microscope and you're looking at it, and then you can barely make out the core, especially on the single mode. On the multi-mode, you can make out the core a little bit better. But the cladding is just used to keep the signal moving along, because there's going to be bends in the cable. There's a requirement for maximum bend radius depending on the type of fiber and the type of connection and everything. But it can't be like a 90-degree angle bend, because the cladding may not do its job then. But for small bends, that's what the cladding is for. It's to keep that signal, it bounces off the cladding and stays in the core. And that's why you can have a small amount of bends in your fiber optic cabling. Okay, up to 10 gigs at 550 meters. That's for multi-mode, much faster and greater length for single mode. I don't know why they didn't put numbers up there, but it can go 10 gigabit, probably on the order of many kilometers. Different connectors. You don't really need to know too much about them, but you saw most of the same stuff in CNT101. Just know that there are different types. And that's what's really expensive about fiber optic. The cabling itself is kind of expensive, but it's really these connectors. Back when I used to terminate fiber, they were $10 to $15 a piece. Whereas, your RJ45 plugs are in bulk a quarter or less. So you screw up on these and you've just, burned $10 to $15. I don't know, haven't looked at prices lately, but that's what they were back in the 90s when I was messing around with them. And, it takes a lot more expertise, equipment, usually a fiber termination kit for field terminations of these types of cables, like outdoor stuff, is going to cost you, upwards of a couple $1,000 or at least over $1,000. And then add in the testing equipment, and it's not cheap to have a outfitted fiber termination kit. And then the connectors themselves are expensive. So that's why we don't have fiber everywhere. If it weren't for that, why use copper with all its problems with EMI, crosstalk? Use fiber, but it's expensive and somewhat you need training to terminate it. And mostly it's expensive. Patch cable, patch cords. Patch cords can actually have pretty tight bend radiuses compared to like outdoor cable, but that's because they're only going short distances. Okay, so this is just, comparing the two, fiber versus copper. And I think I'll stop here because there's wireless, there's, all this bunch of standards to talk about, and it's getting late and everyone's tired, including me. So we will pick up from here on Monday. So we'll probably get through 4 and even into 5 on Monday. I think we might even have 3 chapters to do next week. So that's probably a good thing. And then Wednesday for sure, we'll do labs. And Zoom people, if all we're doing next Wednesday is lab, then I'll let you know that, and you don't need to Zoom in because you don't really want to watch a bunch of people with their backs to you doing labs. But I'm not sure if that's going to be the case. So just look for an announcement in Canvas about next Wednesday, if all we're doing is lab, then you don't need to Zoom in. If we still have stuff to go over in the modules, then you do. Okay. All right. We'll see. Have a good weekend, and we'll see you next week.
Hey, Professor, I got a question before you get off.
Yeah.
So I was looking, when you go to the grade section on Canvas, it has in-class labs week 2, which for some of us that are coming from afar, we'll probably just stack those. And then I see October 22nd, there's the lab submission 2.1, the module quiz 2, the module quiz 3. My question is for the lab submission 2.9.1, when you go to modules, and I just want to clarify, and you go to week 2, I see packet tracer labs, and I see the 2.9.1. But in that section with packet tracer labs, there's also 4 other ones. Are those ones to look at, ones to do? Is that extra?
It's ones that that you should probably that I want you to do, but I'm not having you turn anything in. The only ones that you turn in, the only stuff you'll ever turn in will always be under assignments.
Okay.
In Canvas. So the only packet tracer that you're turning in is the lab assignment 291 and the skills assignment 1, iOS basics. Okay. So both of those are, this is not a lab from Netacad. This is a assignment that I created, the skills assignment 1. And so, you'll do that just like you do labs. The only difference will be, it'll look different and it'll have my instructions instead of Netacad's instructions on what you're supposed to do. And so the thing is for the most part, this first skills assignment, I think, is pretty basic. Probably what's in 291 covers what you need to know for skills assignment 1, but I can't swear to that. It's actually can't remember since last year, but that's why I signed the other packet tracer labs, is
Okay.
that doing all the packet tracer labs, I think is recommended so that you're well prepared for the skills assignments, because they count more than the labs do.
Understood. I just wanted to make sure, like, I was like, where do I? Because I was like, I was seeing all these packet tracer labs, but I wasn't seeing a place to turn them in, and I was like, I'm confused.
Just
So-
under, just the stuff, I usually pick one, sometimes two of the packet tracer labs and put it also under the assignment section. So
Okay.
what I would do when you go to do your labs, your packet tracer labs, look at which ones are under assignments, so you know which ones to really focus on and save and because you'll be turning those in.
Okay. Thank you for clarifying on that. I appreciate it.
Yep, not a problem. We'll see you
All
later.
right. Have a good weekend. Bye, Johnny, Anthony, Jerry, Andrew. See you guys later.
Quick
Well,
question.
Anthony, I'll see you later.
So like basically on my labs, like I was getting like almost like basically everything correctly. I even looked at everything.